The so-called molecular clouds are considered one of the most famous telescopic images. It is important to understand that these are hydrogen atoms, molecular hydrogen gas, or H2, which is the primary form in which hydrogen is found, and that these molecules occupy an absolutely gigantic volume of about 100 million light-years. However, it is not entirely the case, as they are somehow completely dissolved. They really have the form of clouds, and there are places where it is denser and others where it is thinner. Just like we see clouds in the sky, that is how a telescope sees these formations. It is worth noting that as soon as the density rises, gravitational forces instantly appear and start to compress the molecular clouds. Compression in the place where the local density inhomogeneity of these molecular clouds takes place leads to the formation of very loose, but nevertheless large formations, which are not referred to as stars, but quasi-stars or quasars, and represent a kind of body that emits a very narrow range of radio signals, like a star. Therefore, the signals could not easily be detected. These quasars occupy a very large space. But this is no longer a simple cloud, but rather some kind of formation. And then it follows the same formula as that of the birth of a star. This is a cloud, a formation, which consists mainly of hydrogen and helium molecules. When the temperature reaches 10 to the power of 6 Kelvin, and if heavy hydrogen is present, also called deuterium, then this temperature is sufficient for a thermonuclear reaction to take place, leading to the synthesis of helium-3 when two atoms of deuterium combine. This results in helium-3 plus a neutron plus 3.26 megaelectron volt. That is, this reaction is accompanied by the release of energy. I would like to add that there are 10 to the power of -5 deuterium in these clouds. But if this deuterium were not present, we would still reach the same end result. But this reaction would be extremely slow, even if the mass of this star is only 1/10 the mass of the Sun. However, as a result of gravitational compression and a rise in temperature to 10 to the power of 7 Kelvin, not only deuterium but also hydrogen can combine. And hydrogen combining with hydrogen gives deuterium, an electron, a neutrino, plus 0.42 megaelectron volt. But only this combination of hydrogen with deuterium results in helium-3 plus 5 megaelectron volt, and helium-3 plus helium-3 gives helium-4 plus 2 protons plus 12.85 megaelectron volt. It is clear how these interactions at this temperature can lead to the formation of helium nuclei in combination with the release of energy, quite a decent amount totaling 12.85 megaelectron volt per atom. In short, we need 4 protons, and then we can get 1 helium-4, 2 electrons, and 2 neutrinos. And for these 4 protons, we get an energy gain of 26.7 megaelectron volt. Essentially, the hydrogen burns out into helium. Here is a clear summary of the 3 stages. We have already discussed the first stage. At the second stage, helium-3 interacts with helium-4. Again, it turns out that 4 protons give helium-4. And at the third stage, beryllium interacts with a proton with the same results. The combustion of hydrogen is the most crucial point. Hydrogen burns, releases energy, and this energy is spent on the conversion of hydrogen into helium. Now we will see that helium also burns, and that it will also release energy. That is, we first have hydrogen burning, followed by helium until it is burned out. Then carbon will burn, followed by the burning of oxygen. This process will continue as long as energy is being released. The release of energy will end only when we reach iron. When the atomic number is higher than that of iron, reaching nickel, energy will no longer be released. Thus, the process comes to an end. This is the most important stage from the moment when we got hydrogen and helium from protons and neutrons. Immediately after their formation, this is how, after a billion years, the synthesis of heavier elements began, which, in principle, can bring us to iron. It may or may not be successful. It all depends on how much hydrogen we have, essentially, how much fuel we have. If there is little fuel, then we will only reach carbon or oxygen. If there is enough fuel, then we will move on to the next stage. But in principle, we will never cross the border of iron because the release of energy ends here. This is how a star comes into being. The temperature inside is quite high, at 10 to the power of 7 Kelvin. While hot layers rise up and are replaced by cold layers moving inward. Thus, it gains in brightness as it burns. The process is stable, while the formation of helium is ongoing. This is what we will see in space, the burning of hydrogen. Let's consider the Sun as a good example. In the beginning, there were also molecular clouds, followed by the protostar, and then the beginning of a thermonuclear reaction. Today we are somewhere here. We can see this incredibly bright Sun with a temperature of 10 to 15 million degrees Celsius inside. On the surface of the Sun, it is around 6,000 degrees Celsius, which is quite well known. It will burn for about 6 billion more years. When the hydrogen runs out, helium will be formed. At this stage, helium no longer releases as much energy during its synthesis. The star will swell and become a so-called red giant, the loose formation of which is much larger than the original Sun, but the brightness will no longer be the same. It will be cold inside since the hydrogen will only burn on the outside. When this hydrogen burns out, we will get this kind of formation, a very loose and cold cloud. And in the center, there will be a very dense formation due to the intense compression of carbon. The compressed carbon in the middle is what we call a white dwarf. That is the progression from here to here, ending with a white dwarf. The dwarf will be like a white dot in the sky, and then it will eventually turn black, completely extinguished. This is the evolution of a star in which nucleosynthesis, or combustion, or nucleosynthesis due to combustion, did not reach iron due to the lack of hydrogen.